So you've been digging into this whole retrieval-augmented generation thing, huh? RAG. Tons of info out there.
Yeah, it could be a bit overwhelming, right?
Sure. But that's why we're here, I guess. To
Yeah.
kind of filter through it all.
Pull out the good stuff.
Exactly. So
Yeah.
you walk away, feeling like, okay, I get RAG now. I see why it matters.
It's like giving these LLMs, like ChatGPT and all those, a way bigger toolbox.
Yeah, instead of them just relying on what they already know.
Right.
So let's start there. What's the problem that RAG is trying to solve? What's the big deal?
Well, the thing is, LLMs, they can be amazing, right?
Yeah.
But sometimes they can just make stuff up or give answers that are like totally outdated.
Hmm.
But with RAG, it's like we're giving them access to this whole library of up-to-date info.
Like an open book test, sort of?
Exactly.
Okay, cool. So how does it work?
Well, based on all the stuff you sent over, it seems like the basic idea is to take, like all your own documents and make them searchable in this really smart way.
Right.
And then use the relevant parts from those docs to help the LLM give you better answers.
Okay, so it's kind of like combining the LLM's smarts with all this extra knowledge.
Exactly.
That's cool. And it looks like these sources, especially that one YouTube video from that LangChain engineer, they lay out this whole roadmap for RAG,
Yeah.
from like organizing your data all the way to getting these like really reliable answers.
They even use these fancy terms, right? Query translation, routing, query construction, indexing, retrieval, generation, even active RAG.
What?
Lots of moving parts, but it's actually pretty logical once you break it down.
All right, well, let's do that. Break it down. Where should we start?
Well, I think a good place to begin is with indexing.
Okay, indexing. What's that all about?
So indexing is basically like setting up your documents in a way that makes them super easy to search.
Okay.
When you need to find something quickly.
Right. Like a good index in a book.
Exactly.
Yeah.
But here, it's about taking all your raw text. It could be documents, articles, web pages, whatever you got, and turning it into something that a computer can easily understand and search.
Okay, so like, how do you do that?
Well, a big part of it, and the YouTube video talks about this a lot, is transforming that text into numbers.
Numbers.
Yeah, specifically something called vectors. Vectors.
Vectors. Okay, why vectors?
Because vectors, they can capture the meaning of text in a way that just looking for matching words can't.
Right, because words can be tricky.
Exactly, like synonyms and all that.
Exactly. Okay, so vectors. And what kind of vectors are we talking about here?
So there are two main types. First, there are sparse vectors.
Sparse vectors.
These are basically just counts of how often different words appear in a document.
Got it. Pretty straightforward.
Yeah, it's a more statistical approach.
Makes sense.
But then there are dense embeddings.
Dense embeddings. What are those?
These are much more sophisticated.
Okay.
They're created using these, powerful machine learning models that are trained to understand language.
So it's not just about how many times a word appears, but like what it actually means.
Exactly. And they represent this meaning in a fixed length vector, a list of numbers, basically.
So it's like assist and help might have very different sparse vectors, but their dense embeddings would be similar because they have similar meanings.
Precisely.
Cool. So once you have these vectors, what do you do with them?
So before we get there, there's one practical consideration. The models that create these dense embeddings can only handle a limited amount of text at a time. That's their context window.
Right.
So if you have a really long document, you need to break it up into smaller chunks before you can turn those chunks into embeddings.
Makes sense. Kind of like breaking a big task down into smaller, manageable steps.
Right.
Okay, so we've chunked up our documents, turned those chunks into vectors. Now what?
Now these vectors, they get stored in a special kind of database called a vector store. It's specifically designed to handle these numerical representations of text.
Okay, a vector store. So it's not just your regular database.
Right. This one is optimized for searching and comparing these vectors efficiently. And along with each vector, you store a link back to the original text chunk it came from.
Got it. So basically, indexing is all about turning your documents into these searchable vectors and then putting them in this vector store for later use.
Exactly. It's like creating a detailed map of your information so you can easily find what you need.
Makes perfect sense. Okay, so the documents are indexed. They're sitting in our vector store, ready to go.
Right.
Now, let's say I ask a question. How does the system actually find the relevant parts of the documents? The retrieval part.
So retrieval is where the magic happens. It's all about finding those needles in the haystack.
Okay. And how does it do that?
Well, When you ask a question, the first thing that happens is that the system also turns your question into a vector.
Ah, so you're using the same embedding model that you used for the documents.
Exactly.
Like
So
that.
now you have a vector for your question,
Mm.
and you have all these vectors representing chunks of your documents.
Mm.
And then the system performs a search within the vector store. It's looking for the document chunks whose vectors are most similar to the vector of your question.
Okay, so it's comparing the vectors, basically.
Yeah.
And how does it determine similarity?
Well, one common way is using cosine similarity. It's a mathematical way to measure the angle between two vectors in this multidimensional space.
Ooh, multidimensional space. That sounds complicated.
It's a bit abstract, but the basic idea is that if the angle between two vectors is small, it means they're pointing in a similar direction, and therefore they're semantically more similar.
So it's like we've projected all our document chunks in our question into this space, and the ones that are close together are the ones that are most related.
Precisely. It's a powerful way to find meaning-based connections, even if the words themselves aren't exactly the same.
That's really cool. So the system has found the relevant document chunks. What happens next?
Right. So now we have this handful of relevant information snippets, but we're not done yet.
Right, because we need to actually get an answer to our question.
Exactly. And that's where the prompt comes in.
Okay, the prompt.
This is where we tell the LLM what to do with this retrieved information.
Got it.
A prompt is basically a template. It has these placeholders or slots where we insert specific information.
Okay. And what kind of information goes into these slots?
Well, typically you'll have a slot for the context,
The context.
and that's where the retrieved document chunks get inserted.
Okay, so the LLM gets to see all the relevant background information.
Right. And then you'll have another slot for your question.
Okay, so it knows what it's supposed to be answering.
Precisely. So the system takes those relevant documents, drops them into the context slot. Your original question goes into the question slot, and that whole filled-in prompt is what gets sent to the LLM.
So it's like saying to the LLM, hey, here's some info. Now, based on this, answer this specific question.
Exactly. It gives the LLM the context it needs to generate a grounded and reliable answer.
And I think I remember seeing something in the LangChain stuff about an expression language, LCL.
Yes, LCL. It's super useful for this whole process.
Yeah.
It lets you easily connect all these different pieces like the prompts, the LLMs, the retrievers, and even some tools for parsing the LLM's output.
So it's like a way to streamline this whole R-grade workflow.
Exactly. And we even saw some examples, right? Like a simple prompt template that was just a couple of sentences. And then there were those more complex prompts from that prompt hub.
Right, but the main idea was the same. Give the LLM the context and the question.
Precisely.
Okay, cool. So we've indexed, we've retrieved.
Right.
Now for the moment of truth, generation. How does the LLM actually take all that info and spit out an answer?
So this is where the LLM really gets to flex its muscles.
Right.
It takes all that context you've provided, along with your original question,
Yeah.
and uses its sophisticated language understanding to generate a response.
And this response is hopefully based on the provided information, not just some random stuff it comes up with.
Exactly. The beauty of RAG is that the answers should be grounded in the data you've given it, not just its pre-existing knowledge.
Okay, so that's the basic idea, right? Retrieve relevant info, feed it to the LLM, get a grounded answer.
Right. But the stuff you sent also talks about all these advanced RAG techniques that can make the whole process even better.
Oh, yeah, like ways to fine-tune it.
Exactly. Especially in that retrieval step.
Yeah.
Making sure you're getting the most relevant information possible.
That's where that whole query translation idea comes in.
Yes, query translation is key.
Okay, so tell me more about that. What is query translation and how does it help?
So the idea is that sometimes the initial question you ask, it might not be the best way to find the info you need.
How so?
Well, maybe it's too broad, or maybe it doesn't use the right keywords, or maybe it just doesn't quite match how the information is structured in your data.
Right, because the way we think about something and the way it's actually organized in a database might be different. So query translation is all about tweaking our question before it even hits the vector store.
Exactly. It's about making sure our question is as precise and effective as possible.
Cool. So what are some of the ways to do this query translation?
There are a bunch of different techniques, but one really interesting one is multi-query.
Multi-query. Okay, what's that about?
So instead of just using your original question, the system takes your question and automatically generates several different variations of it.
Oh, that's cool. Like rephrasing it in different ways.
Exactly, and often from different perspectives.
Okay.
The idea is that one of these alternative questions might be a better match for the relevant documents in your vector space.
Right, because different phrasing might lead to different results.
Exactly. And then each of these rewritten questions, they're all used to perform separate searches. And the unique documents retrieved from all these searches are combined.
Ah, so you're casting a wider net, so to speak.
Precisely. And that way, you increase your chances of capturing all the relevant information.
I like it. Multi-query.
Yep. What else?
So another technique that builds on multi-query is called RAG fusion.
RAG fusion. Okay.
It starts the same way as multi-query, generating multiple queries and doing separate searches for each.
Uh-huh.
But the key difference is what happens next.
Okay, what happens next?
It uses this really clever ranking technique called reciprocal rank fusion.
Reciprocal rank fusion.
Yeah, it's a mouthful.
For sure.
But what it does is it takes all the rank lists of documents from those different searches and combines them into a single unified ranked list.
Oh, interesting. So it's not just about getting more results, it's about intelligently combining those results.
Precisely. It helps prioritize the most consistently relevant documents from across those multiple searches.
That makes sense. So multi-query is about breadth, getting a wider range of potential results. And RAG fusion adds this layer of smart ranking on top of that.
Exactly.
Cool. What else do we have in our query translation toolbox?
Well, another useful technique, especially for dealing with complex questions, is decomposition. Decomposition. Break it down.
Exactly. So instead of trying to answer a big, complicated question all at once, you break it down into smaller, more manageable sub-questions.
Okay, so it's like dividing and conquering.
Precisely. Each of these sub-questions can then be used for retrieval, and then the answers to those individual parts can be combined to give you a complete answer to the original question.
Ah, so it's like solving a puzzle one piece at a time.
Right. And there's also this related idea of parallel answering, where you tackle independent parts of a larger question simultaneously.
That's interesting. So if my question has multiple parts, I can address each part individually and then put it all together in the end.
Exactly.
Okay, decomposition. What else?
Well, sometimes you need to take a step back before you can move forward.
Mm.
And that's where step back prompting comes in.
Step back prompting.
Yeah. So imagine you have a question that requires some background knowledge to understand.
Mm.
Instead of directly answering that question, step back prompting is about first asking a more general, higher level question to retrieve that necessary background information.
That's smart. So you're essentially building a foundation before you try to answer the specific question.
Precisely. It's like making sure you have all the pieces of the puzzle before you try to put it together.
I like that. So step back prompting helps to handle questions that rely on some underlying concepts.
Exactly.
Okay, any other cool query translation tricks?
Well, we've got one more, and it's a pretty wild one. Hypothetical document embeddings, or HI-E for short.
High E, huh? Sounds mysterious.
It's a bit of a mind bender.
All right, lay it on me.
Okay, so imagine this. You ask a question, right?
Mhm.
And instead of immediately searching for documents, the LLM actually tries to generate its own answer first, or even a short hypothetical document.
Wait, so the LLM is trying to answer the question even though it hasn't seen any external data yet?
Exactly. But the thing is, this hypothetical answer, it might not be accurate.
Right, because it hasn't seen the real information yet.
Exactly. But it often captures the essence of what you're looking for, the key concepts and ideas.
Okay.
And then this hypothetical answer, it gets turned into an embedding.
Ah, okay, so it's like you're creating a vector representation of this imaginary answer.
Precisely. And that embedding is what gets used to search for real, factual documents in your vector store.
So you're using the LLM's internal knowledge to guide the search in your external data. That's fascinating.
Yeah, it's a pretty clever way to bridge the gap between the LLM's knowledge and your own information.
I love that. Using the LLM's best guess to point it in the right direction.
Exactly.
Okay, so we've talked a lot about how to refine the question itself, but what about routing? You mentioned that earlier. How does that fit into all of this?
So routing becomes really important when your RAG system has access to multiple data sources.
Multiple data sources, okay.
Right. So maybe you have different vector stores for different types of information, or maybe you also have a traditional database, or even a graph database. The point is, the information you need might be spread across different places.
Right, so it's not just one big haystack anymore, it's multiple haystacks.
Exactly. And the purpose of routing is to figure out which haystack is the right one to search.
Okay, so it's about intelligently directing the question to the most appropriate source. How does it actually do that?
So there are two main approaches. One is logical routing.
Logical routing.
Yeah, and this is where you essentially tell the LLM what kind of data is in each source.
Uh-huh.
And then the LLM uses its reasoning abilities to decide which source is most likely to have the answer.
So it's using its smarts to figure out where to go.
Exactly. Like, okay, this question is about customer data, so I should probably check the customer database.
Makes sense. What's the other approach?
The other approach is semantic routing.
Semantic routing.
And here, you take your question and embed it, just like we talked about before.
Yeah.
But you also have these embeddings or descriptions associated with each of your data sources.
Okay.
And then the system compares the question embedding to the source embeddings and routes the question to the source whose embedding is most similar.
So it's kind of like finding the closest match between the question and the descriptions of the sources.
Precisely. It's all about semantic similarity.
Got it. So logical routing is about using the LLM's understanding of what's in each source. And semantic routing is about comparing the meanings of the question and the source descriptions.
Exactly.
Cool. So we've talked about query translation and routing. What about query construction? How is that different from just translating the query?
Okay, so query construction, it's about going a step further than just rephrasing the question.
Okay.
It's about taking a natural language question and turning it into a very specific, structured query.
Structured query.
Right, like something a database can understand.
Uh-huh. And why would we want to do that?
Because sometimes you need to leverage those specific capabilities of your data source,
Mm.
especially if you're dealing with metadata.
Metadata. Okay.
Metadata is like the information about the information.
Right, right. Like the author of a document or the date it was published.
Exactly. So let's say you have a vector store full of research papers,
Uh-huh.
and each paper has metadata, like the publication date, the authors, and the topic.
Okay.
Now, if you ask, find me recent papers on quantum computing by Dr. Smith,
Mm-hmm.
query construction is about turning that natural language question into a very specific query that your vector store can understand.
So it's not just searching for the words quantum computing and Dr. Smith anywhere in the document.
Right, it's going a step further.
Okay.
The structured query would say, okay, I want documents where the topic is quantum computing, the author is Dr. Smith, and the publication date is within a certain range.
Ah, so you're being very specific about what you're looking for.
Exactly. And you're leveraging the metadata to make your search much more precise.
That makes a lot of sense, especially if you have a lot of data.
Exactly. And the cool thing is, LLMs can help with this too.
Really? How so?
You can use something called function calling. You basically provide the LLM with a description of the metadata fields that are available and how they can be used for filtering.
Uh-huh.
And then the LLM can analyze the user's question, extract the relevant criteria, and format it into a structured query that the vector store can understand.
Wow, so the LLM is essentially writing the query for you.
Exactly.
That's awesome.
It's pretty powerful stuff.
Okay, so we've covered a lot of ground here. We've talked about how to refine the question itself with query translation, how to route it to the right data source, and how to construct more precise queries using metadata.
Right.
But we also touched on something earlier about indexing strategies beyond basic embedding. Can you tell me more about that?
Yeah, so beyond simply embedding chunks of your documents, there are more sophisticated ways to structure your index for even better retrieval.
Okay, interesting. Tell me more.
One technique is multi-representation indexing.
Multi-representation indexing.
Yeah, and the idea here is to separate the actual content of your documents from what you use for retrieval.
Okay, I am intrigued.
So, for example, you could use an LLM to generate a really concise summary of each document chunk.
Uh-huh.
And then you embed that summary for retrieval.
Okay,
The full document chunk is still there, but it's stored separately.
got it.
And then when a relevant summary is retrieved, you fetch the corresponding full chunk.
Ah, so you're retrieving based on a condensed version, but you still have access to the full information when you need it.
Exactly. And this can be really helpful when you're working with long context LLMs.
Right, because those LLMs can handle more text at once.
Exactly.
Okay, multi-representation indexing. What else?
Another interesting approach is called Raptor.
Raptor!
It sounds intense.
It stands for Recursive Abstractive Processing for Trees Optimized Retrieval.
Okay, I'm going to need you to break that down.
Yeah, it's a mouthful. But basically, it's a hierarchical indexing method.
Hierarchical indexing. Okay, so what does that mean? It's about creating a tree-like structure of your documents with different levels of abstraction.
Levels of abstraction.
Yeah, so at the lowest level, you have detailed chunks of your text.
Uh-huh.
But as you move up the tree, the content becomes more summarized and abstract.
Okay, so it's like an outline with different levels of detail.
Exactly.
How does that help with retrieval?
Well, it allows the system to handle both very specific granular questions that might be answered by a small chunk and more general high-level questions that require information from larger
It
sections.
was flexible.
Exactly. And it's especially useful for navigating very large documents without having to split them up too much.
Okay, so Raptor's all about organizing your information in this hierarchical way.
Right.
And you mentioned one more technique, course, right?
Yes, course.
Mm-hmm.
It stands for Contextually Optimized Association of Relevance in Sentence Embeddings.
Wow, another mouthful.
I know, right?
So what's course all about?
It's a bit different from the others. It's not about structuring the index itself, but about how you calculate the similarity between documents.
Ah, okay.
We talked earlier about cosine similarity, right?
Mm-hmm.
Well, course uses a different algorithm that's designed to better capture the contextual relationships between sentences, especially in longer documents.
So it's a different way of measuring how similar two pieces of text are.
Precisely. And research suggests that it can lead to better retrieval accuracy in some cases.
Interesting. So it's like a different lens through which to view similarity.
Exactly.
Okay, so we've covered a lot of ground here with these advanced indexing and retrieval techniques. It's amazing how much thought and research has gone into optimizing this part of the REG process.
Yeah, it's really a fascinating area.
Now, the last thing I want to touch on is this concept of active REG and sophisticated flows. You hinted at this earlier, and it sounded like it involves the LLM taking a more active role in the whole retrieval process.
Yeah, so active RAG, it's about moving beyond that simple linear flow of retrieve, then generate.
Okay, so it's not just a one-shot deal.
Right. It involves the LLM making decisions along the way.
Decisions, like what kind of decisions?
Well, for example, it might decide whether retrieval is even necessary based on the question.
Ah, so it might be able to answer the question directly from its own knowledge?
Exactly. Or it might evaluate the quality of the retrieved documents and decide to re-retrieve with a modified query if they're not good enough.
So it's like a feedback loop. The LLM is constantly checking and refining its approach.
Precisely. And the key idea here is the concept of a state machine.
A state machine. Okay, I'm not familiar with that term.
So instead of a fixed sequence of steps, imagine a system that can be in different states.
Okay.
And it can transition between these states based on certain conditions or the results of previous steps.
Okay, I think I'm starting to get it. So it's like a more dynamic and adaptable workflow.
Exactly.
Can you give me an example of how this might work in practice?
Yeah, so there's this paper called CAG.
CAG.
Yeah, it stands for Corrective R.
Okay, corrective RG. So it's about correcting mistakes.
In a way, yeah. So imagine this. The system retrieves documents, right?
Huh.
But then it actually grades those documents for relevance.
Grades them.
Yeah, like how well do they actually answer the question?
Okay.
And if they're not good enough, the system can actually retrieve from an external source, like the web.
Oh, wow. So it's not limited to just the data it already has.
Exactly. And then finally, it generates an answer.
So it's like a multi-step process with checks and balances along the way.
Right. And there are tools like LangGraph that are specifically designed to help you build these complex state machine-based arg flows.
Okay, so LangGraph is like a framework for active RG.
Exactly. It gives you the building blocks to create these more sophisticated workflows.
Cool. And you mentioned something about unit tests within the arg flow.
Yes. That's the concept of online flow engineering.
Online flow engineering.
Right. So it's about adding these checks at various points in the process.
Okay, so it's like testing things along the way.
Exactly. Like automatically checking if the retrieved documents are relevant to the question, if the generated answer makes sense, if it actually addresses the user's query.
Makes sense. So if something goes wrong, you can try to fix it.
Precisely. And some models, like Cohere's Command R, they're really good at this kind of active R.
Oh, really? Why is that?
Well, they have really good support for using external tools and for making routing decisions, so it's much easier to build these adaptive RG systems with all those checks and conditional steps.
Got it. So ActiveArgy is all about building these more intelligent and adaptable workflows using tools like LangGraph and models like Command R.
Exactly.
But I imagine these more complex flows also come with some trade-offs, right?
You're right. They can be more computationally expensive.
Right, because there's more going on behind the scenes.
Exactly.
So you might have to be more careful about the models you use and how many iterations you allow.
Precisely. It's all about finding the right balance.
Now, one last question that I think a lot of people are wondering about. With all these advancements in long context LLMs, do we even need RAG anymore? Can't we just feed the LLM all the relevant information directly?
Yeah, that's a great question, and it's one that a lot of researchers are exploring right now.
Right, because LLMs are getting better and better at handling large amounts of text.
Exactly.
So what's the answer? Can long context LLMs replace RAG?
Well, the answer, unfortunately, is not so simple.
Okay.
The materials you sent talked about this interesting concept of a multi-needle haystack.
Yeah, the multi-needle haystack. That sounded like a pretty important experiment.
It is. So basically, they take these very large pieces of text, like a haystack,
Uh.
and they embed specific pieces of information throughout, like needles,
Uh-huh.
and then they test the ability of these long context models to retrieve all those needles.
Okay, so it's like testing how well the LLM can find specific pieces.